Hello again. This video is associated with this diagnostic test, and we happen to be on question 11, 12, and 13. So we're going to squish these all on one video. Starting out with question 11, let's zoom in. A study found the correlation between the height of men and the height of their sons to be 0.71. So that makes sense. If I know the height of a grown man, can I use that to predict the height of their son? That makes sense. Now they're asking, what is R? So really they're asking for a script here. They tell us R. What does R squared mean in the context of the problem? So R squared, let's go ahead and calculate that. If R is 0.71, then R squared would be 0.71 times 0.71. So using my easy calculator, I don't really need a fancy calculator, I get the value 0.50. So right off the bat, I'm going to eliminate A and C and E. Now, taking a second look at the problem, I think about the script that I memorized from class. So we know our script says this. Our script says if I know R squared, I can say that 50% of the variability from the least squared regression line, when using that, can help me explain the variable of X on Y. So I think about which one sounds like the same script that I'm used to hearing. And that pretty quickly makes me think this is not the script at all, and this sounds really similar to the script. So it says 0.5 is the proportion of the variability. Well, that's what 50% is, a proportion, 50 over 100. So it's the proportion of the variability in the sun's height that can be explained by the approximate linear relationship. So that's another way to say the least squared regression line between the father's height and the son's height. So I'm definitely going to pick D. Now let's look at question 12. I'm loving it because they're talking about R once again. Now this is kind of a cool question. It seems almost exactly like one we did in class. We know R is when we have two quantitative variables. So I'm just going to jot that on the side. So that's going to be my dead giveaway. In the last question, I definitely had two quantitative variables, meaning 2 units. I measured the men's height in inches or centimeters. I measured their son's height in inches or centimeters. So those are 2 quantities. So I'm going to look through here and see if I can find some sneaky categorical data that's trying to throw me off. I look through here and I see political affiliation. I also see gender. So I'm going to circle those and cross out B and cross out C. I also see race, so that's not, okay, so that just doesn't make sense. The other thing I notice is that all of these, R doesn't have a unit of measure. R is merely a value how close the dots are to the line. It can be positive or negative, but it has to be between 1 and -1. Uh-oh. On A, it's not between 1 and -1. So I'm going to write that on the side. It must be between, R must be between -1 and +1. And they kind of broke that rule on A. So I'm going to eliminate A just on that. I think I'm going to eliminate A for other reasons, but definitely right off the bat for that. Here, now it says R squared, or excuse me, R is 0.58, so that's reasonable. Now it says R is 0.5 miles per gallon. Uh-oh, no. R does not have labels, so I'm automatically going to eliminate E, because they added a label, or also known as a unit of measure. We know that R does not have a unit of measure because it's merely measuring the closeness of those dots. So if I've eliminated everyone except D, which is my answer. Now let's go to the next question. Here we go again. It's a design question. So let's take a deeper look. It looks like they're designing an experiment. And so I want to make a quick jot about how I go about designing an experiment. So when we reviewed, at the bottom of my paper, I'm just going to pull some notes out of my notebook. I noticed a page in my notebook that looked like this. I thought, oh yeah, that's handy. I'm going to reference that. It said, I need to be, step one, when I design an experiment, I need to be specific about my random treatment. Or excuse me, my random method is what I'm getting out of my notes. I need to be specific about my random method. That's the first thing I got to do. Next, then, once I randomly make sure that everything's been randomized, then I give the treatment. But I got to be specific about that. So I got to be real specific about who and what gets the treatment. And then if I did a good job there, my last step is, again, very specifically, I'm hoping to get some type of measurable results. So that's really my 3 steps when I design an experiment. And each time I'm very specific about how I'm doing this. Now when I look in the question, they said, compare. So they said, you came up with a new way to treat a cloth for flame retardant. So kind of like a Halloween costume. We want those to be resistant to getting caught, catching fire. So you found a new way to do that. However, we're going to need to compare that to probably the old. So they said, you've been given 2 types of fabric to see if in fact it is better than the current one we use. 100 pieces come from each type. So it looks like you're going to get 100 samples of the old and 100 samples of the new type. So now I can be a little bit more specific down here on my picture. I want to make sure that both my old fabric and my new fabric get exactly the same treatment, but whatever that treatment is, I want to make sure they each get it. All right. So I'm assigning retardants, certain retardants on these fabrics. Interesting. So that means 100 of those fabrics would get the old retardant, and 100 of the fabric would get the new retardant. And that's important because I want to be random and accidentally give all of this new treatment to the old fabric. That's not gonna work out for me. The other thing is, of course, the number one word here is random. So as I read through my choices, A says I'm going to assign 100 pieces with the new material. I don't see anything about that being random. You're just assigning it. So I'm going to cross out A because it fails for not being random. B says you're going to take a number, 0 to 99, so that's nice. And on that first type of fabric, it looks like half of them are going to get the one treatment and half of them are going to get the other. So I actually like that right off the bat. The only thing that could maybe make B a bad answer is if in fact the numbers, the random numbers you selected don't total up to 100. So I look at that and I say to myself, does the number 100, are there 100 numbers within here? And I notice that there are 99 numbers. and then the number 00 would be the 100th number. So I like that. There are 100 numbers here. And as I read through, it appears as if I did separate. I randomly assigned the first 50 for one treatment, and the ones that didn't get selected go to the other. And that sounds a lot like the scripts we memorized. So I'm liking B. I'm ultimately just seeing if the other ones fail for some reason or another. So as I look at C, I'm noticing they never once say the word random. It doesn't appear that each piece had an equal chance of either getting the old retardant or the new. So I don't like C because it's not random. Okay. Now D. Again, flipping a coin is a way to make sure that each had a 50-50 chance of getting chosen. But if I flip a coin and if I get heads, I get one treatment, I may in fact get a lot more heads than I end up getting tails. And so that's too scary because I might result in a bunch more getting one type of treatment. And I don't want that. So I don't like D. So B is looking better each time. Now E, select one types of fabric, all 100, flip a coin. If it comes up heads, assign the old flame, and the new get the other. Once again, it doesn't appear as if each one had an equal chance of being chosen, since they're all going to the one assignment. So I'm picking B. Thanks for tuning in.